In today's lesson, we're going to mix things up a bit. Normally, I give you a bunch of puzzles to solve, but today, I'm mostly just going to ask you to sit back and relax while I tell you a story. I hope you'll find it an intriguing story, since it involves a very special puzzle. This puzzle has a name. It's called the hardest logic puzzle ever. It's a fiendishly difficult variation on the sort of question puzzles we considered in our last lesson. However, before I can tell you the story, I need to introduce you to a piece of logical machinery we've not had an occasion to discuss before. So let's get that out of the way right now. In Lesson 4, we discussed logical connectives such as not, and, or, and if-then. Let's recall specifically what we said about if-then statements, meaning statements where we say if P, then Q. We decided that a statement of this form should be considered false when the first part is true and the second part is false. We also decided that such statements should be considered true in any other circumstance. Statements of the form if P then Q are typically referred to as conditional statements, or just conditionals for short. Now, one thing about conditional statements is that you cannot generally switch the order. In other words, the statement if P then Q is usually different from the statement if Q then P. For example, the statement if Spot is a normal dog, then Spot has 4 legs is true. But if Spot has 4 legs, then Spot is a normal dog is false. But sometimes you want to say not just if P then Q, but you also want to say if Q then P. We capture this idea by using the if and only if connective. In other words, if I say P if and only if Q, you should take that to mean the same thing as if P then Q and if Q then P. You can think of this assertion as saying that P and Q are logically equivalent. They always have the same truth value, either both true or both false. So the statement P if and only if Q should be considered true when P and Q have the same truth value, either both true or both false, and false otherwise. Statements using the if and only if connective are referred to as biconditional statements, since they really involve 2 separate conditional statements. We're almost ready to begin, but let me make one final note. We call this the hardest logic puzzle ever for a reason. Some of the details will get pretty hairy later on. I promise that as we go along, it will not be necessary to work through every detail of every scenario we'll consider. You'll be fully able to follow the story as long as you get the gist of what's being claimed. That ends the setup. Time to get down to business. Are you comfortable? Is your popcorn ready? Good. Let's begin our story. The hardest logic puzzle ever was introduced by philosopher George Boulos in a paper published in 1996. The paper was called The Hardest Logic Puzzle Ever. The puzzle is this. We are to imagine 3 gods. The gods are named true, false, and random. True only makes true statements, and false only makes false statements. But random is a wild card. Each time he's asked a question, he mentally flips a coin, and depending on the result, he decides whether to answer the way true would answer or the way false would answer. Your task is to determine which god is which by asking no more than 3 yes-no questions. However, there's another complication. Though the gods understand English perfectly, they will answer in their own language. In this language, the words for yes and no are da and ja, but you don't know which word means yes and which word means no. So there you go. You have 3 yes-no questions, but you don't know who you're speaking to, and you won't know what his answer means. What can you do? Let's clarify a few points before we continue. It's perfectly fine to direct more than one question to the same god. In other words, it's not required that you direct your questions to a different god each time. Also, you don't have to have all three of your questions worked out in advance. It's fine to ask a question and then to let the answer to that question determine your next question. Now, like all good stories, this one seems to have an innocent beginning. No doubt it's a difficult puzzle, but we've seen difficult puzzles before. Eventually we'll come to the solution, and then that will be the end of the story, right? Ha! Let's have a look at Boulos' solution. Since his solution was very complex, he built up to it in stages. Specifically, he used some gateway puzzles to build up to the main event. Here's the first of those puzzles. Imagine that I place 2 aces and a jack face down on the table in a row. I know which card is which, but you don't. Your task is to point to one of the 3 cards and then to ask me a single yes-no question. I stipulate in advance that if you're pointing to an ace, then I'll answer your question truthfully, but if you're pointing to the jack, then I'll answer either yes or no, completely at random. What can you ask me so that, based on my answer, you'll be able to definitely identify one of the cards as an ace? This puzzle has a similar flavor to those from our last lesson. You might want to pause the video here to use what you learned there to work out this puzzle. Are you ready for the solution? Here we go. One question that works is to point to the middle card and to then ask, is the left card an ace? Let's consider the possibilities. Suppose you're pointing at an ace. Then, according to the rules, I'll answer truthfully. If I now say yes, then the left card is an ace. And if I say no, then the right card must be the second ace. But suppose you're pointing at the jack. Then I'll answer randomly. But that's okay, since in this case, the left and right cards are both aces. So if I answer your question with yes, then you won't go wrong by assuming the left card is an ace. And if I say no, then you won't go wrong assuming the right card is an ace. Do you see the point? Regardless of what you're pointing at, you can interpret yes to mean the left card is an ace and no to mean the right card is an ace. And I only ask you to identify one card as an ace. Problem solved. This shows how we can sometimes extract useful information even when our conversation partner might be behaving randomly. But now things get more complex. Here's Boulos' second warm-up puzzle, essentially as he presented it. Suppose that, somehow, you have learned that you are not speaking to random, but instead are definitely speaking to true or false, but you don't know which. Further assume that the God to whom you're speaking has condescended to speak in English. Suppose you need to know whether or not Dushanbe is in Kyrgyzia. What one yes-no question can you ask so that the response will definitively resolve that issue? We'll come to the solution in a moment, but first, let me clarify this business about Dushanbe and Kyrgyzia. First, Kyrgyzia is the former name of the small country today known as Kyrgyzstan. Dushanbe is actually the capital city of the neighboring country of Tajikistan. Therefore, Dushanbe is not in Kyrgyzia. I deliberately left the puzzle essentially as Boulos stated it, as an illustration of the sense of humor of some academics. As we'll see, Boulos is about to establish the principle that if we know we're not speaking to random, and if the gods answer in English, then we can ask a single question of the gods to determine whether or not any particular factual assertion is true. A normal person might use something simple, like 1 + 1 = 2, as an example of a very basic fact claim, but Boulos instead amused himself by picking something incredibly obscure. Anyway, if you want to take a shot at this one, then pause the video here. Here's the solution. We can ask the question, are you true if and only if Dushanbe is in Kyrgyzia? Now, this question involves a biconditional statement. Its 2 parts are, 1, we are speaking to true, and 2, Dushanbe is in Kyrgyzia. If these 2 statements have the same truth value, both true or both false, then the true answer to the question is yes, and the false answer to the question is no. Now, we already know that Dushanbe is not in Kyrgyzia, so item 2 is false. Knowing that, what will true say if we ask him this question? Well, he'll reason that item 1 is true in this case, and therefore that the truthful answer is no, and that's what he'll say. And if we address the question to false, well, he'll reason that item 1 is false, and therefore that the truthful answer is yes, and he'll lie and say no. In other words, regardless of whether we're speaking to true or to false, the answer will be no. But just for the sake of argument, suppose it were actually true that Dushanbe is in Kyrgyzia. In this case, item 2 would be true. How would the gods respond this time? Well, this time, true would reason that both items are true, meaning the truthful answer to the question is yes, and that's what he'll say. But if we're talking to false, then he'll reason that item 1 is false, meaning the truthful answer to the question is no, but then he'll lie and say yes. So regardless of whether we're speaking to true or to false, the answer will be yes. Which brings us to the best part. Suppose we use X to represent any factual assertion whose truth value we wanted to know, and suppose that we know that we're not speaking to random. Then we ask, are you true if and only if X? If X is a true statement, then both gods will answer yes. If X is a false statement, then both gods will answer no. For example, suppose we want to know if the road we're driving on will take us to the city. We could ask, are you true if and only if the road takes me to the city? A yes answer means it will take me to the city, while a no answer means it won't. Now, I went through those possibilities very carefully to illustrate the sort of case-by-case analysis that will become increasingly important as we go along. However, I think we'll quickly drive ourselves crazy if we constantly stop to analyze every case for every scenario we'll consider. So for the rest of the lesson, you're welcome to pause the video periodically to work things out for yourself, or you can simply take my word for a few things as we go along. Okay, back to the story. The principle that we just discovered, that biconditional statements can be used to get direct answers to direct questions, so long as random is out of the picture, continues to work even if the gods answer with da and ja. To see this, suppose you're definitely talking to true, and suppose X represents some factual assertion whose truth value we wish to know. We can ask, does da mean yes if and only if X? It turns out that an answer of da means that X is true, and an answer of ja means that X is false. Now, you'll need to consider 4 cases to verify this. The statement X is either true or false, and da either means yes or no. The analysis of the cases proceeds in a manner nearly identical to what we've already seen. But let me repeat the main point. When X is true, the true God will answer da regardless of whether da means yes or no, and when X is false, he will answer ja regardless of whether ja means yes or no. We now have what we need to understand Boulos' solution to the hardest logic puzzle ever. Remember, our challenge was to determine which God was which by asking no more than 3 yes-no questions. The true God only makes true statements, the false God only makes false statements, and the random God sometimes answers truthfully and sometimes answers falsely. But remember, the gods will answer in a language in which the words for yes and no are da and ja, but you don't know which word means yes and which word means no. Now, since Boulos' opening question is the most complex, and since the second and third questions are simpler, it will be convenient to consider his questions in reverse. Let's label the gods A, B, and C. Suppose we've learned B's identity and that we know that he's not random. We can now ask him, does da mean yes if and only if A is random? If we know that B is true, then we're in precisely the situation we considered a moment ago, where A is random is playing the role of X. An answer of da now means that A really is random, and an answer of ja indicates that actually C is random. If we know that B is false, then the logic will be reversed, but we'll still be able to identify random, and that will effectively solve the problem. In this scenario, we already know B's identity. Our question definitively identified which of A and C is random, and then we'll know that the remaining God is true. Now we back up one step. Suppose we've definitively identified B as a non-random God, but we don't yet know whether he's true or false. We want to identify B definitively. In other words, is he true or is he false? We can use the solution of our second puzzle to ask, does da mean yes if and only if 1 plus 1 equals 2? As we've seen, since 1 plus 1 equals 2 is known to be true, an answer of da implies we're speaking to true, while an answer of ja implies we're speaking to false. So all that's left is to find a first question that definitively identifies one God as not random. It's actually this step that causes most of the complexity. For this purpose, Boulos came up with this. We'll let X be the assertion, you are true if and only if B is random. And we now ask A, does da mean yes if and only if X? In other words, does da mean yes if and only if you are true if and only if B is random? Now, if you care to work through the logic, you'll find that there are many cases to consider. A is either true, false, or random. B is either random or not random. And da means either yes or no. To simplify things for a moment, let's assume that A is not random. Then the possible cases are shown in this table. Surveying the table, it turns out that if A is not random, then an answer of da means that B is random, and an answer of ja means that B is not random. Either way, we've identified someone who is definitely not random. And if A is random, well, then we're right back in the scenario considered in our first puzzle. Even if A is random, we won't go wrong by interpreting da to mean that C isn't random, and we won't go wrong interpreting ja to mean that B is not random. Okay, let's take it from the top. Boulos' solution is to start by asking God A, does da mean yes if and only if you are true, if and only if B is random? The answer to this question definitely identifies one of the gods as not random, let's say B. We then ask B, does da mean yes if and only if 1 plus 1 equals 2? This will tell us for certain whether B is true or whether B is false. And then we ask B, does da mean yes if and only if A is random? And then we're done. Whew. You can see why Boulos called this the hardest logic puzzle ever. What we've seen is all very ingenious, but it sure is an awful lot of hard work. In fact, it's so much hard work that we might wonder if things are really as bad as all that. Do we really need these very intricate, nested biconditional questions to get the job done? This leads us to the next part of our story. In 2001, philosopher Tim Roberts pointed out that a much simpler solution is possible. It turns out that we don't need Boulos' intricate questions after all. We can get by with just standard if-then statements. If you recall our discussion of the heaven-hell puzzle, you'll recognize the techniques Roberts used. His solution uses the same strategy as Boulos. Use the first question to identify one of the gods as definitely not random. Use the second question to determine which of true or false this god is, and then use the third question to find the identities of the other two gods. Here's how he did it. First, we go to God B, and we ask, if I asked you if God A was random, would you say da? Let's consider two cases just to see how the analysis goes. Suppose B is true. Let's also suppose that A is random and that da means yes. With these assumptions, if true is asked if A is random, then he'll reply with yes. And since da means yes, true will indeed reply with da when asked whether A is random. So B's answer to the conditional question is da. Now continue to suppose that B is true and A is random, but now assume that da means no. Again, true will answer yes when asked if A is random. That means saying ja. So B's answer to the conditional question is no, since he will not say da when asked if A is random. Thus, B will again say da in this scenario. It can be difficult to keep track of all the cases, but if we suppose that B is true, then the cases work out like this. The point is this: if B is true, then a response of da tells us that A is random, and a response of ja tells us that A is not random. And if A isn't random, then C is. Incredibly, it turns out that this conclusion holds even if B is false. That is, a case-by-case analysis shows that if B is not random, then a response of da implies that A is random, and a response of ja implies that C is random. And if B is random, then, as before, we won't go wrong assuming that either A or C is not random. And just like that, we've succeeded in our goal of finding a God who is definitely not random. Let's suppose that God is C. Roberts now suggests asking C, if I asked you if you always told the truth, would you say da? This question will tell us whether or not C is true. The possible cases are shown in this table. A response of da means that C is true, and a response of ja means that C is false. The final question is again directed at C. This time we ask, if I asked you if B was random, would you say da? This will solve the problem. The possible cases are shown in this table. Now, I remember once spending the better part of an afternoon working through all these cases. If you have the patience for it, there's something truly beautiful about how everything works out just right. What matters for us, though, is that final column. A response of da tells us that B is random, and a response of ja tells us that B is not random. It's like a magic trick. Now, as I've said, it's not so important to work through each and every case. What is important is that we've dramatically simplified the solution. Instead of using intricate biconditional questions, it's sufficient to use normal conditional questions instead. But perhaps we can simplify things still further. After all, Robert's solution, while simpler than Boulos's, is still pretty complicated. It turns out that we can do much better. The saga continues. The next part of our story came in 2008, when philosophers Brian Rayburn and Landon Rayburn simplified things still further. They noticed something that had been missed in prior solutions to the puzzle. We've been assuming that no useful information could be gleaned from speaking to random, since we've no idea how to interpret anything he says. But this is not necessarily true. For example, suppose we go up to any god and ask, have you ever told a lie? True will truthfully say no, and false will lie and say no. But remember that random always answers either as true would answer or as false would answer. In other words, he doesn't just answer randomly, saying yes or no as though he hadn't even heard your question, but rather decides randomly whether he'll behave like true or like false. That means random will always answer no to this question. This opens up the possibility of getting direct answers to direct questions even if we're talking to random. And Rayburn devised a way of doing just that. Their solution doesn't require wasting the first question on just finding one God who's definitely not random. Instead, they suggest asking God A, if I ask you if you are true in your current mental state, would you say ja? And it turns out that regardless of who you're speaking to, a reply of ja indicates he really is true, and a reply of da indicates that he's either false or random. Let's say it turns out that A really is true. Then we can ask effectively the same question of B, and his answer will definitively identify him as well, thereby solving the puzzle in just two questions. If instead we know only that A is either false or random, we just use our second question to ask, if I ask you if you are false, would you say ja? This will definitely identify A, and then we can use our third question to repeat the process with B. As always, it's not so important that you chase through every possibility. Rather, it's the progression of ideas that's important. Boulos used difficult, nested, biconditional questions. Roberts noticed that normal conditionals are sufficient, and this simplified the solution considerably. But then Rayburn devised a fundamentally different approach, which made it possible simply to get useful answers to our questions, regardless of who we're speaking to. This is what it's like to work in an academic setting. Each researcher brings his own ideas to a problem, gradually improving and building upon the work of others. So, have we reached the end of our story? Not even close. There's much, much more. For example, you might be wondering what the big deal is about using 3 questions. Why can't we do it in 2? Well, Rayburn and Rayburn found a way of doing just that, though their method was based on taking advantage of an ambiguity in the way Boulos initially stated the problem. And then we can wonder about making the hardest logic puzzle ever even harder. What if random were really random? In other words, what if he really did just answer your question as though he hadn't heard what you said, instead of always behaving either as true or as false? These are interesting questions, and much has been written about them. This is a long and winding saga, and we've seen only a small portion of it here. But for now, we'll call it a day. See you next time.